So welcome to the third colloquium in this semester's series, and we're extremely proud and privileged to have a very special guest here, Jenny Greene. Many of you will know a lot about her and her work. So without any further ado, I'm going to hand over to Nadine, Jenny's host, for the formal introduction.
Just in time for introductions here. So it's really a tremendous pleasure to introduce Jenny Greene from Princeton here to Heidelberg. And Jenny actually, she received her PhD from Harvard, but working a lot with Louis Ho in California, and then was hired directly out of grad school to Austin, Texas on a professorship, assistant professorship, but she delayed that start for a Carnegie Princeton fellowship. And so she spent some time in Princeton and she liked it so much. So then she moved to Austin eventually, but came back to Princeton on the faculty. Yeah, so she is in Princeton on a faculty position since 2011, right? One of the maybe like most senior people there in terms of, how long you've served on the faculty there. So, and also like Jenny's doing amazing work on black holes, also massive galaxies, a very broad interest. And now she will talk about the little red dots that JWST is seeing in large quantities. But also Jenny is an awesome person, just like that. And she's founded and also is now running as a faculty director, the Prison Teaching Initiative in New Jersey, which is like a great initiative. So Jenny, please take it away. It's a pleasure to have you.
Thank you, Nadine. I guess you can hear me, yes? Yes. Well, thank you all for having me. Thanks for coming. We won't talk about the first slide, but voting has started in the United States. I'm not saying dwarf galaxies are Democrats, but before I get into the little red dots, I do want to advertise just very briefly the other side of my research life, because some of my students on the dwarf galaxy side also have been doing amazing work. So for most of my talk, I'll be discussing what may be some of the densest objects in the universe. So just to give you a well-rounded colloquium, we'll start with very diffuse, very low mass things within 10 megaparsecs. And then we'll get to the JWST little red dots. So yes, this is the elves and dwarfs part of my talk. And the motivation for this work really has long been the promise that dwarf galaxies are so dark matter dominated that these could be the best probe of dark matter on small scales. And of course, many challenges to cold dark matter have arisen from observations of dwarf galaxies. But as always, I think we find that we're still fundamentally limited by our understanding of the baryons. And so our contribution has been to build group catalogs for Milky Way analogs within the local volume. So this is our ELVES survey here. So many of the dwarf searches and much of our understanding of the low mass end of the halos have come from the Milky Way and M31. And the idea was to diversify the groups that we can study by looking at larger volumes. And so we and this complementary SAGA survey have been working on this for the last few years, and I wanted to show you some highlights. I'm not going to go too deep because I want to spend most of my time on the little red dots, but so Scott Carlston, who really is the heart of the ELVES survey, had the realization that surface brightness fluctuations are an incredibly cheap way of getting distances to low mass dwarfs. So before Scott started his thesis, there were 6 Milky Way-like galaxies, including the Milky Way and M31, that had well-characterized dwarf systems down to classical dwarfs, so few times 10 to the 5 in stellar mass. And typically what you would do to get the distances is you would find a bunch of faint fuzzy friends that might be associated, and then you go to Hubble and you get TRGB distances, or in the case of SAGA, you'd get 1,000 radial velocities to find for associated dwarfs. And so what Scott realized is that surface brightness fluctuations you can do from the imaging themselves, and you can very efficiently get distances and build these dwarf galaxy catalogs quickly. And so the way the SPF works is, of course, in any image of a galaxy, we're mostly just seeing the very brightest stars. And so you can see Poisson fluctuations from pixel to pixel in the number of bright stars. And if you take the same galaxy and you move it further away, you get more stars in a pixel, and so those Poisson fluctuations go down. So if you can measure the power on the scale of the PSF, then you can get a handle on the distance, which of course also depends on the number of bright stars. So you have to have some handle on the stellar population, which we just calibrate with a single optical color. And SPF has long been used for, few percent distances to massive elliptical galaxies. And Scott's insight was even in dwarfy galaxies with more complicated star formation histories, we can get 15% distances. So he got TRGB, SPF for TRGB dwarfs and calibrated the SPF. And then that allowed us to do 30 of the 31 Milky Way plus Milky Way and more massive hosts within 11 megaparsecs. So that was ELVES. This is the kind of money plot if you want. So this is the richness of each group. So the number of satellites down to 5 times 10 to the 5 in stellar mass and out to, let's call it the virial radius. We don't quite get there all the time. And you can see that when you sort the systems by the mass, here the stellar mass, but okay, we could make up a halo mass if you want, that the scatter in richness that we observe is pretty well what you would predict from CDM. There had been some intriguing suggestions that maybe there were lower richness groups than expected, but we think for the whole sample that it's pretty good. You can also figure out how the group environment impacts the galaxies. So we did an exploration of the quenching as a function of mass. Saga made a lot of, oh dear, Dominica, I was hoping I was not going to break your pointer. The squares are Saga, and they made a lot of headlines by suggesting that the Milky Way satellites, which are no longer forming stars, are more quenched than the typical Milky Way analog in Saga. In ELVES, we really reproduce the amount of dwarfs which are non-star forming as a function of the mass of the satellite. So that's that black curve. We can go a little further because we have nearly 400 satellites. And if we just take a model of the infall distribution times, we can ask how long it takes to quench, presumably by ram pressure stripping, as a function of the mass of the satellite. And you can see that it is, perhaps unsurprisingly, faster to quench lower mass systems and starts to take close to a Hubble time as you get to the most massive satellites. And then also Scott was able to look at the mass size relation for the satellites. What I guess other people had known, but I found surprising, is that both the non-star forming and the blue satellites have exactly the same mass size relation. So whatever it is that shut off their star formation does not change their structure appreciably. We also looked at the globular cluster and nuclear star cluster populations, but I won't get into it. So the last thing I'll talk about briefly before leaving the dwarf galaxies behind is this new program led by Josh-Wan Lee, who is a graduate student with me in Princeton. And the idea is to take the same approach, use SPF, but look for dwarf satellites of dwarf hosts, which has been done only for a very small number of systems, these 5, including the LMC. One host at a time. It's very hard because the number of background faint fuzzy friends doesn't change, but the number of satellites goes way down. And so our efficiency is much, much lower, but we're doing this. And this will be the sample. So we're aiming for 40 dwarf hosts. He's got 5 measurements. Those are the red. He's got another 20, either archival HSC data or Magellan and Gemini follow-up, and the pink and gray are predictions from our stellar to halo mass relation from ELVES, and so that's what we think we can do. And here's hot off the press our last discovered dwarfs. This host is, I don't know, 3 times 10 to the 8. And lo and behold, we have a beautiful, I don't know, we see a booming SBF signal here if you like to do SBF with your eye. So it's clearly at this distance of 5 megaparsecs. So this is fun because I don't think this is going to be much less massive than the host. We're also finding these dwarfs in the field. So this Josh Wan named the hedgehog, and it's just serendipitously discovered in the legacy survey. Again, you can see that modeled look to the image that tells you that it's pretty nearby, even with decals imaging, which doesn't have a great PSF. And we know the distance, so we can say that it's pretty isolated and it is not forming stars, at least for the last gigayear. So it is possible for 10 to the 6 solar mass galaxies to shut off their star formation, at least for a bit. All right, so I'm going to skip these next 2 and pause if there's any dwarf galaxy questions. Otherwise, we can engage on that later, and I'll go to little red dot. All righty, awesome. Okay, so now we're going to the other side of the universe. Redshift 5 to 7, compact red sources, which might be accreting black holes or might be very massive compact galaxies. We can take a vote at the end if you want. I want to acknowledge my collaborators who dragged me into the world of JWST, which was very much not in my plan. I didn't know JWST was going to eat my life, but it's been wonderful and fun. Mostly through this Cycle 1 Treasury program Uncover, which is led by Rachel Bazanson and Ivo Labe. But there was a lot of critical infrastructure work done by Sedona Price, John Weaver, Bingji Wong, and these are all postdocs. So please pay attention to their work. They've done a great job getting this survey. All of the catalogs are public, and we hope you will do science with Uncover. There are also 3 other programs. 2 of them are in Abell 2744, the Uncover field. That's a Hubble Frontier field. So Ren Cease had a Cycle 2 follow-up program. We have all 20 near-cam bands, broad and medium. And then Rohan, Naidu, and Yorit Mathi have this GRISM program in the Uncover field. So all of this will come up at various times in my talk. And then, of course, someone you probably know, Anna de Graaf, has a Rubies program, one of the few spectroscopic follow-up programs where you can both understand, and she does, in fact, understand the selection function of her spectroscopy. So that's an awesome thing. Okay, so there's 2 pieces of context for my talk. I teach my students that massive galaxies formed their stars early and rapidly. We know this from archaeology of low, redshift 0 elliptical galaxies. But I don't know, you probably imagined, I did not imagine just how fast and how early that might mean. So this is a redshift 5 gorgeous prism spectrum from Rubies that seems to have formed its stars very early, redshift 10. So yeah, that's faster than I was imagining. I was sort of thinking 3 to 5, and JWST is telling us it was even earlier. And right after the Sears data came out, Ivo Labe published this paper, which could be the progenitors of these redshift 5 massive quiescent things. These double break or V-shaped galaxies appear to show a Balmer break at redshift 7, and the implied masses got up to 10 to the 11, redshift 7 to 8. And so, people started to claim this was breaking CDM because maybe there aren't even enough massive halos to host such massive galaxies. My parents started calling me, wondering what was going to happen to the universe. So that was one piece of context. We sort of have the opposite problem for black holes. I never paid attention to high redshift quasars in my past life, but it turns out that if you look at UV or X-ray selected quasar populations, they are way depressed compared to the galaxy populations. So we all know that UV selected quasars are rare, but at any other redshift below 5, you can find vigorous black hole accretion in something like 10% of galaxies. But suddenly, above redshift 5, the fraction is dropping like a rock. And so just to drive this home, this is from Eduardo's review. Okay, so this is like the entire sky. People working since 2000, and there are 531 UV selected quasars above a redshift of 5. And this has actually been a problem for the modelers because you have to actually stop the black holes from growing too early or accreting in order to reproduce this apparent dearth of accretion. Okay, so that is the context in which these compact red sources started to get on my radar. And so I guess the next important realization came from Dale Kochevsky, who presented this broad H alpha line for one of EVO's apparently redshift 7, 10 to the 11 solar mass galaxies. And this thing is at redshift 5 and has broad H alpha, from which we implied that it was not a 10 to the 11 solar mass galaxy at redshift 7.5, but rather an accreting black hole at redshift 5. And these things started to show up in all of the deep fields. So this is really similar SED to Evo's paper, but let me just spend a little time here. So a rising continuum in the rest frame optical, rising in red, and then a little bit of blue light in the UV. This is from Guillermo Barro's paper. And so we started to find these things also in Uncover, and Jort and Rohan dubbed them little red dots because they are very compact. Okay, so this is our favorite triply imaged little red dot from Uncover. It was one of the first papers that we published actually just from the NIRCam imaging. 2 of the images were actually known from HST. We found the 3rd image. It's strongly lensed, magnification of 6. So there's a size limit of 30 parsecs on this thing. And you can see the photometry here. So again, rising red continuum in the rest frame optical. It's at redshift 7. So there's H alpha right off the prism, and then a little bit of very faint but blue light in the UV. Very strange SED. So even from the photometry, we were claiming that this is likely an AGN because of that small size and because of that strange but quite red SED. And then 8 months later, Uncover got 700 MSA spectra in some cases very deep. This is a very deep spectrum because we got deep integrations on all 3 images. And then we saw very clear evidence for broad H beta, so 2,500 kilometer per second. So yeah, rising red continuum, broad Balmer lines, faint and blue rest UV, and this change in slope, which we'll talk about quite a bit more in my talk, so that we sometimes call a V-shape. There are other properties that these broad lines are often characterized by absorption, Balmer absorption, which is very rarely seen in low redshift quasars and implies very high density gas because effectively it's acting like a resonance line. So you need high enough densities to trap Lyman alpha. And then you see this only in less than 1% of low redshift quasars. And here from one of Anna's first rubies, you see this beautiful absorption in helium-1. So how do we find these things? We've selected them photometrically. I showed this already from Sears. We also have a photometric sample from Uncover. Here's Guillermo Barro's paper. They have also been found spectroscopically with GRISM data. So this is the paper that coined the term little red dots. But what's critical to me actually is that these sources were basically purely selected to have broad H alpha and all turn out to have the characteristic SED of a little red dot. So they are the brightest population of broadline selected AGN, or broadline, not AGN, broadline selected things with JWST. Why are there so many people writing proposals for little red dots that I can't get my time? This is because of the demographics. They're very common. Okay, so this is the luminosity function of UV selected quasars, which basically flattens at low luminosity. These are galaxies, and these are the little red dots. So they are something like 100 times more common than UV selected quasars, and something like a few percent of the galaxy population. And roughly speaking, we say that 20% of broadline selected AGN with JWST show this characteristic V shape. To try to make the number densities a little more visceral, on the right, I'm showing our attempt at a bolometric luminosity function. We'll talk about their SEDs in a while. So we don't really know their bolometric luminosities, but these are scaled broad H alpha. Okay, so that's the best we can do. And we don't have to worry about all the lines. I'll direct you to this black line here. This is if you imagine putting an accreting black hole in every halo at redshift 7, that would be your bolometric luminosity function. So we're not really that far away from that. So we're just from the little red dots implying very high duty cycles. So this is the other reason that they're a bit puzzling. Yes. So usually when I say AGN, I just mean any accreting black hole. And usually when I say quasar in this talk, I mean something that was selected in the rest frame UV. but yes, there is a luminosity difference as well. It's somewhat arbitrary exactly where you put that luminosity difference, though. I mean, if you select in the UV, then you don't have very much choice to have much SED variation because you have to be bright in the UV. I mean, Eduardo can say more, but typically they look very similar at redshift 6 as they do at redshift 2. So with Uncover, we have the somewhat unique experience that we selected a photometric sample from the NearCam Uncover data. And then we spectroscopically followed up 12, including the triply imaged thing. And so we have a little bit of demographic information about where these things fall in color space. So we confirm broad lines for 9 of the 12. We also got 3 gorgeous deep brown dwarf spectra, which Adam Bergasser has written a very nice paper about, and I'm not showing here. So this box is just the V-shape selection from that original Labe paper from Sears. So this is really about as red as you can be in NearCam 277 minus 444. And this blue cut says you have that little bit of UV excess. Okay. Already 30% of those are showing broad lines. If you additionally add a compactness criterion and a second color, so you get rid of things that just look red because they have line boosting, but actually the continuum is not red, at least 80% are showing broad lines according to our Uncover spectroscopic follow-up. And so a large fraction of things that JWST is finding in this red color space are compact and have broad lines. These things seem to go together. We know little about the redshift distribution. It's much easier to find them at high redshift where you have a clear Lyman break, but Dale Kochevsky has tried to quantify this and has shown the number densities falling dramatically below a redshift. So we had this moment in August 2023, after spending a year putting together our photometric sample of little red dots, we got all of these broad H-alpha lines. And I felt really good because I thought they were AGN. And then we found these broad lines and I thought broad lines must be accreting black hole. And then everything got more complicated. So now I'm going to tell you about that. So we started to look at the SEDs more broadly. We collectively, not me. This was our 1.1 millimeter imaging from Seiji Fujimoto in Uncover. And so already you can see on the left are star-forming galaxies. These are not compact, but they have actually pretty similar V-shaped SEDs as little red dots, but they're extended, they're vigorously star-forming, and they're very well detected at 1.1 millimeters. That's 30 Kelvin dust associated with the star formation. The little red dots, on the other hand, when we apply this compactness criterion, these are point sources at 444. They are undetected individually and in a stack at 1.1 millimeters. And in fact, we used that as one of our arguments that these were likely to be AGN, with much hotter dust. But then Christina Williams put together SMILES data, so MIRI data out to roughly rest frame 3 microns. And while the little red dots are typified by a rising red continuum in the rest frame optical, and we thought this was going to be duck soup to detect them with MIRI, that they would just be getting redder and redder. Instead, we never see hot dust. Both in stacks and individual sources, they turn over and become flat in F nu at wavelengths past 1 micron. So this is what all or most normal AGN do. This is 1,000 Kelvin dust in a torus. Little red dots don't have it. Nor do they seem to have X-ray. So I was raised that all accreting black holes make X-rays, that we were going to find all the high redshift AGN with links. That does not work for these. So in Uncover, we have 2 megaseconds of X-ray data. We say they're roughly 10 to 100 times fainter individually than we expect from the H-alpha. But this is a stack now of only spectroscopically identified little red dots in Fresco, and so goods north and south. So Chandra, 7 megasecond Chandra data. And I heard rumors that they may have a detection now after multiple rounds with a referee, but if so, it's very faint. And that as of now on the archive, it's a non-detection. Hollis Aikens put together a beautiful broadband SED. This is now 500-ish photometrically selected little red dot candidates in Cosmos Web. So they have less color information, but nevertheless, you can see clearly in the stack that characteristic V shapes. That's the rising red continuum, and then flattening in the mid-infrared, and then nothing. Nothing in the X-ray, nothing in Herschel. I mean, maybe that's not surprising. Nothing in the radio. So then you start to really doubt yourself. So now we only see evidence for the AGN in the broad H-alpha. That's it. No X-ray, no hot dust. And the SEDs look unlike any other GN spectrum we've ever seen. So maybe there's a clue from the spectroscopy. And this is our triply image friend again, and this is my other favorite little red dot. We internally call this the monster because it's 22nd magnitude at 444. And in both cases, so here's this V shape, but you see that this characteristic change in slope, it sort of looks an awful lot like a Balmer break. You know, stars do this at 3,600 angstroms, they turn over. And so we thought, maybe we're seeing Balmer breaks in these things. And so Bingji modeled both Ruby's 1 and Ruby's got spectra for some of the original universe breakers. And she did all of this modeling where she fits the break with the Balmer break and then has an AGN component to go along with the broad H-alpha. What David Seton, who's a postdoc at Princeton, has been working on with the Ruby spectra, so now many, many prism spectra, is just doing a selection in the spectra directly. So he looks for things that are red, have red continua, and very high equivalent with H alpha. Okay, and this is what they look like. And then he just basically fits this region, and he separates things into, do you have a spectral change or not, agnostic to what wavelength exactly that spectral change occurs at. And what he's able to show, and it's easiest to see in the stack, is that this V shape is happening always at 3600 angstroms where you ionize N equals 2 hydrogen. So we think that's an important clue. So either this is in fact stellar light and this is a Balmer break, or it's dense gas and it has something to do with ionizing N equals 2. This is our conclusion. I'll also show Elon Ma's attempt now to model again the triply imaged source, for which again we have very high signal to noise spectra in the rest frame UV and rest frame optical. Our original picture when we only had photometry was that we were just seeing a reddened AGN that was explaining the steep red slope with a little bit of scattered light. We see this at lower redshift. But this absolutely cannot fit the spectroscopy, because if you try to make a sharp break with a combination of power laws, you simply cannot do it. So this model, I think, is killed both because you can't fit the spectra and because you would not expect to always see the spectral change at the same wavelength. It would just depend on how red the quasar is and where the scattered light comes in. All right, so that model is dead. You can fit the SED as a 200 mega-year galaxy. So this is like an A star. So there was star formation, but now it's a post-starburst. Remember, this thing is smaller than 30 parsecs. This will be a few times 10 to the 9 in stellar mass. Feels a little uncomfortable. A lot of stars in a small space, but you can model the spectrum that way. However, we do have broad H alpha and broad H beta to explain. And if you do the whole continuum with stars, then what is photoionizing the lines? So we don't love that model either. So we thought, can we make a combination of stars and AGN that would fit this spectrum? And you sort of can, except for it's completely galaxy dominated, because anytime you add any power law at all, you can no longer reproduce the strength of the break. And we tried all different kinds of underlying AGN models, redder ones, super Eddington ones. And the only real way to fit this SED with the model set that we have is with a pure stellar continuum. There's really just no room for power. This is not so different, I think, from the conclusion that Bingji came to. And so we basically now have these two pictures. On the one hand, the things are very compact and they have broad Balmer lines. And so these properties seem to suggest an accreting supermassive black hole. On the other hand, we don't have a natural way of explaining the full SED. Of course, AGN show a range of SEDs, but these are systematically different across the board from those that we know from lower redshift. Or perhaps they're just stars. That would be natural given that their UV optical continuum looks like stars. Josephine Bagan has a paper pointing out that if you put 10 to the 11 solar masses of stars within 50 parsecs, then the broad lines could just be the virial width of that system. You still have to photoionize the lines, which I think they don't have a solution for, but nevertheless, it's true that at those densities, which are very high and not seen in other systems in the universe, you would indeed expect 2,500 kilometer per second lines. So here we are. If they are black holes, then we have maybe some extreme conclusions. We've selected them to be point sources, which puts some limits on the stellar mass that can hide under the AGN. I've tried to stay away from showing black hole masses because I really don't think you can measure a reliable black hole mass in these things, given that we don't understand their SEDs. But if you blindly take the broad line and imagine it's coming from a BLR whose size is similar to lower redshift things, then we infer very high ratios of black hole to galaxy mass, 1% or higher. So this is from Vasily's redshift 8.5 size, sitting way above local scaling relations. And of course, this is our highest redshift 1 at redshift 8.5. And so it's, again, challenging to grow such a seed unless you're very comfortable with super Eddington, or you start your seed pretty massive. We are, as I said earlier, pushing close to a very high duty cycle, just taking the little red dots alone. And if you take our luminosity functions, it actually does help explain the amplitude of PTAs. So we would really like to know if these are black holes. On the other hand, if they're galaxies, they're really some of the densest stellar systems that we've ever seen. So this is from Josephine's paper. And a lot of the stellar mass in the universe at redshift 7 would be in these galaxies, although it's talking with Anna earlier. I'm not exactly sure how to compare number densities, and we maybe haven't done all the calculations we need to, but the number densities of the little red dots are pretty high. Okay. Any other clues? So one of the things I'm really excited about doing is trying to push to lower redshift with ground-based searches. So I'd like to get to redshift 2, where we could explore the hot dust challenge out beyond 3 microns. And so Elon has been looking through our hyper supreme camera imaging, which gets to 26 in or 27 in the observed optical, so that gets us the rest frame UV at redshift 2, and then we have nice matched near-infrared imaging across about 20 square degrees, and then Spitzer IRAC. So he's got a set of candidates, and the day after the JWST deadline, we were able to fit in 2 hours with fire on Magellan, thanks to David Seton. This is the only object we've spectroscopically followed up so far. And you see it has the SED of a little red dot, and it has beautiful broad lines, and it has super duper narrow O3. So I'm quite hopeful that we're going to now have a very nice, robust sample of relatively bright things at redshift 2 that we could get easier follow-up to fill out the SED. The other nice result from URIT that's not quite published yet is the clustering. So this is using the GRISM data, the alt data, and the uncover field. The black line here is the little red dots. This is just basically poor man's clustering, counting how many friends each of them has in the GRISM data. And then the lines are how different stellar mass galaxies cluster, and the punchline is that the little red dots on average are clustering like the orange line, which is 10 to the 8 solar mass galaxies. So that seems important. And perhaps at odds with the stellar continuum only picture. Okay. I'm doing fine on time, right? Okay. So I'm going to spend a couple slides going back to our favorite bright little red dot. This is at redshift 4.5. And again, because Ivo was the PI of Uncover, he got extraordinarily deep spectra, 3 different MSA pointings, I think 15 hours of integration with the prism. So I'm not even showing the whole H alpha line here, but you can see it's actually quite rich in the UV because the equivalent widths are high. So the H alpha equivalent width, here's the alt spectrum, is 800 angstroms. Typical Sloan quasars have 200 angstrom equivalent widths in the H alpha. So that's another thing that's different about the little red dots. And you can see the Balmer absorption there, 100, 200 kilometer per second narrow absorbers. What we see uniquely here, because it's such a bright source and we have such high signal to noise, this is broad iron 2. So quasars have this broad iron 2 pseudo continuum. It seems like it's a telltale signature of an accreting black hole in this one particular bright little red dot. We also have all of the far UV lines. We have nitrogen 4, we have nitrogen 3, carbon-4, carbon-3. So it seems to be nitrogen enhanced and all that fun stuff. Well, but not all of the little red dots are having the same SED. There is a lot of diversity. So this friend and the triply image friend both show almost no metal lines. Both of them show that very prominent Balmer break-like feature. So it's not clear that they're all the same, but they do seem to share a lot of characteristics. We're just getting our ALMA data on our monster friend. Really wanted to detect them in ALMA. We got band 7 and band 9 for the monster. Band 7 has C+ at redshift 4.5, so we have no C+, which means less than 10 solar masses a year of star formation. We have no continuum, which seems to rule out some range of expected black bodies if you take the stellar only model for the optical continuum. This is all just happening in the last week and a half, but David Seton is working on writing this up. So it seems like it's hard, at least naively, to explain a galaxy only model with these upper limits. That's the 1.1, that's the band 7, 1.1 millimeter. Unless you make the dust quite hot, 80 Kelvin or hotter, which maybe you can do because it's very small, but is also not a thing that we've seen in other galaxies. So, almost done. My favorite crazy picture that I think breaks the least things about the universe is that actually these weird SEDs are caused by a little bit of super Eddington accretion, that we are seeing accreting black holes, but that the black holes are not that massive. So they're maybe 10 to the 6, and they're a little bit brighter than they should be because they're a little bit super Eddington, which makes them red. And that weird spectral shape is actually from opacity, Balmer absorption in dense 10 to the 4 Kelvin gas. The X-ray weakness is naturally explained, I'm told, by theorists in super Eddington situations, maybe from a wind, maybe your corona is not as vigorous. And we no longer have a number density problem, because if I can pull from lower mass halos and I'm just a little bit super Eddington, then I no longer have to have crazy duty cycles. And Irene Lambridis has a recent paper exploring the super Eddington idea. I'm going to skip our super Eddington cartoon because you can ask me about it if you want. So here are 2 pictures again, accreting black hole or stars. What can we do next? Well, variability is an obvious expectation if you're powered by an accreting black hole. AGN vary, stellar systems would not. So we tried various ways in cycle 4. Maybe someone will like our proposal. And then the other thing, of course, is if the Balmer break is a Balmer break, we ought to see stellar absorption. From the PRISM data, we don't have high enough spectral resolution to do that. But we put in a bunch of medium resolution near spec proposals in different configurations, hoping to see if there's stellar absorption in the continuum. And then in our low redshift sample, we can really hope to get out to 10 microns and see if there is hot dust. It's just a little bit colder. So that brings me to the end. I can take questions first, or I can show the fun last slides. Okay, I'll stop there and take questions.
Thank you very much. What a mystery. We have a big audience online as well as here in the auditorium. So those online, if they want to ask questions, please raise your hand or type something in the chat, and I'll take the first questions from the floor. If there's a student here who wants to actually pose the first question, please go ahead.
Hey, thanks for the cool stuff. So you showed the clustering plot of trying to compare LRDs with your 10 to the 8, 10 to the 7, 10 to the 9 gas galaxies, but presumably the comparison ones, the sizes are much bigger, or?
That's right. Yeah,
Okay.
those galaxies are typically resolved by JWST.
But you don't really try and select based on sizes to compare either.
No,
No,
no, they're mostly, I mean,
quite typical.
we have spectroscopic redshifts for all of them.
Yeah,
So
but
their
they're
nature is not
typical
so
sizes,
ambiguous.
basically. Yeah. Okay.
They don't have broad lines. They look like galaxies.
Okay.
Okay. If no more questions from students. Student question here? No. Okay, then we'll take students from the general audience. I think Keith was one of the first.
Yeah, I was wondering when you were talking about the millimeter upper limits, right? And then you were looking at different temperatures, black bodies. But isn't the stronger constraint on how much dust there is? I mean, I just don't really understand how you interpret those upper limits.
That's a good question. I don't really, I mean, mostly I just want to cry because I was hoping to detect them. But the calculation that we're doing here simply says to fit the break in the rest frame optical, you really need a pretty narrow range of stellar ages, 100 to 300 million years. So we would still expect quite a lot of heating of dust. I suppose it's true that if there is actually no dust, then that would be another way to get non-detection. The problem with no dust is that we need an AV of about 1 to take the 100 million year SED natively and make it red. So it's actually pretty constraining how red it is, redward of the break. So what David has done is he has taken the combination of AV of 1 that we infer and the age that we infer, and there is a little bit of degeneracy between the age and the AV, but not a whole lot under the ansatz that only stars are explaining the SED. If you take away dust completely, I mean, I don't have a strong opinion about the dust laws are a little bit weird.
Yeah, I was wondering also maybe the dust composition.
Yeah, so the shape
that could change the opacities, right?
The slope that we need ends up being pretty steep, even just for the galaxy only. So we definitely have some issues, I would say, under that galaxy only ansatz. But I do think we cannot fit them there without dust in the rest frame optical. And so then I think it's not unreasonable then to turn that into a limit. But the temperature, however, I can't say can't be 80 Kelvin, and the thing is 50 parsecs or less because it's unresolved.
Okay, I think Hans-Walter Rix had a question, and I'll come to the front.
Thank you, Jenny, for laying this out so beautifully. I wanted to ask about 2 statements you made. The little red dots are among the densest galaxies or stellar systems we know.
If they were pure stars.
If they were pure stars, and their space density is fairly high. What I may just have missed is how do their space densities compare to, say, L-star elliptical galaxies nowadays, and how do their actual densities, if they're all stars, compare to the dense 10 to the 8 solar masses of an L-star elliptical?
So the Baggin plot is meant to answer the second question. So redshift 2 ellipticals, stars only. So it's about a factor of 10.
But the local ellipticals is within the density within the effective radius, or the very essential?
Redshift 2 because they don't have the outer part. So this would be, you know, this is Mariska's.
Yeah, but if I took the inner 100 parsecs of local L-star ellipticals, what would the densities be? Would they also?
It's quite similar to this.
Okay.
Yeah. Now, of course, our resolution is slightly better. So it's a little bit still of an extrapolation.
Thank you.
You asked me a second question.
The first question was, how does the space density compare to L-star early type galaxies?
Day?
Yeah.
Much lower.
Okay. So
But it's a few percent of L-star-ish galaxies at redshift 5.
so it would be plausible if they were to hide as the centers of particularly dense present-day ellipticals, which is an annoyingly naive,
So-
projection to the present epoch.
I feel like there's something we should be able to figure out with the number densities, but it's squishy. One thing is they don't evolve very much from 5 to 7. Another thing is you do have to pump them up very quickly. If you want to make Anna's galaxy between 7 and 5, you really have to have a cataclysmic event to get the densities to be lower. Also, one imagines they would evolve dynamically very, very rapidly.
Okay. Question at the front.
Thank you. You said you have spectroscopy for all of your LRDs,
No,
but
no, no.
no?
I have
For
some
most-
spectra.
Some, because you showed some observations at redshift 9 to 10. And there's probably no spectroscopy there. And can you say something about these events?
Our highest redshift thing selected with our color selection is at redshift 8.5. It has broad H beta.
So 9 to 10, you can say nothing.
There are claims in the literature of photometrically selected little red dots at redshift 9 from Kevin Henlin, and maybe others, but to my knowledge, there are no published spectroscopic little red dots at 9. It's getting very hard to get a broad line. Even H beta is way less commonly broad than H alpha, which we see in AGN at all redshifts, probably because you can collisionally de-excite the H beta or reddening, either way. So as you're going to such high redshift, you would basically need Miri spectroscopy to find the broad line. And to my knowledge, that's not been published. Certainly we're not doing.
Okay, there's a question at the back. We still have some minutes. I beg your pardon? Well, the people online can hear if I bring the microphone.
Thanks for the nice talk. I have like several questions, but you don't have to like do the keep long answer. But first question is like, so I just want to understand like how the high density make the broad H alpha in the galaxy. And second, so you say the Balmer jump is very significant in that kind of galaxy, which means the galaxy have the Balmer, yeah, but which means anyway, so also have a Balmer absorption line, which means that galaxy have a like the abundant level to population and the hydrogen. So which means you probably find something signature of the 2-photon decay in the UV. So I just wonder that point. And then third, had you observed the Lyman alpha together with the H alpha, also Lyman alpha have a broad component or not? That is my question.
I'm not sure I understood the first one. In terms of the Lyman alpha, we see Lyman alpha in emission in about 50% of the, redshift 5 to 7 things that we have the prism spectra for. There's absolutely no way I could figure out if the shape of that Lyman alpha line, because it's at R of, I don't know, very low, 10, 50, whatever it is down on the UV side of the prism. So I don't know the Lyman alpha shape, and I don't think any of the medium resolution spectra are deep enough to see the Lyman alpha. So, or even necessarily have the Lyman alpha in. But can you re-ask the question about?
Yeah, the basically first question is how high density does the environment make broad H alpha? What is the powering mechanism of that broad H alpha? It's
If
red.
it was an H1, then it's broad light region, right? So that would be very high densities. But you wouldn't need it to be bigger than, light months.
But
So that's the way regular black holes solve this compactness problem, by having a black hole. So then you have 10 to the 7 or 10 to the 8 solar mass singularity. And then you have the broadline region is very tiny. I mean, the amount of mass in the broadline region is less than 10 to the 5 solar masses in mass. So it's fine. You just have these broadline region clouds. They're dense, but they're tiny, right? And then they're photoionized by the accretion disk. That would be the standard picture.
Okay.
If you try to do the whole thing in the galaxy scale, then you're talking about 50 parsecs of dense gas, and that's a whole different game.
Okay, we're coming to the end of the question time. Is there any last? Here you are.
Thank you very much. I wanted to ask about the lower redshift counterparts. What was the argument of Kochevsky to say there's not many redshift below redshift 4? And what are you guys changing? Is new data or something that people have simply not looked at?
He's using, I think, 6 near-cam broadbands. And he's using this, I think, quite clever double slope model to the broadbands. But he's fixing the photo Z. So I don't know for sure. I mean, I think that intrinsically that they are rarer at redshift 2 for sure, but I also think he must be missing things because the photo Zs probably get very bad when you lose the Lyman break in JW. And because as the break is moving bluer, you're having not enough constraint on the blue side. My guess. So there were serendipitously, there's 4 prism little red dots that were not targeted as such in a pretty small area already in the archive. So they can't be that rare, I think. And then the very first object that Elon followed up was a little red dot. So I think, I think people have been pitching them in the past because they don't have the wise excess. So no one thinks they're an AGN.
Okay, I think we got 2 more questions, one from here and then the last one from Dominica.
Hi, Jenny. I'm just trying to kind of make a mental picture of like what it would be the AGN structure of these kind of things if they are AGN. You seem to see some of the coronal lines maybe for some of them. I don't know if
we see neon 5 and helium 2 in the monster. And I don't think we have the signal to noise to say much else. I mean, I showed there are a handful that have really no metal lines, like very weak O3. And the equivalent widths of the Balmer lines are lower in those. But in the rest of them, I mean, so that bright guy is 22nd magnitude at 444. I mean, it's very bright. The typical one is 2 to 3 magnitudes fainter, and then much, much fainter in the UV. So we don't, I think, have good constraints on the coronal one.
Yeah, okay. It's just, for me, then it's just, it will be like strong winds that it would like push. I mean, like that's will like destroy the dust.
Absorption. There's definitely outflows. Those are 100 to 200 kilometer per second velocities. And those densities have to be very high, 10 to the 9 or something.
Would you expect then in this kind of accretion mechanism, like to see some jets maybe then for these kind of things?
Well, we don't see them in the radio.
Okay, we're going to be hard pressed to solve what they are this afternoon. But the last word from the audience comes from Dominica.
Thank you, Jenny, for the talk. I think my question goes along the same lines. If they were super Eddington accretors, do you know what that would imply for the structure of the broadline region and what these broadlines would actually be telling us?
I have absolutely no idea.
Because I imagine that.
So I mean, I can show you our super Eddington cartoon if you want, but I don't understand it. Yanfei Zhang understands it. It's his simulation. So when you have super Eddington accretion, I think the theorists all agree that the disk puffs up and you're not very efficiently radiating photons from that puffy part of the disk. There is supposed to be a funnel here. The wind is coming out here. And so, you're having high accretion here in the midplane and you're having an outflow here. So that's how you're allowed to do super Eddington. And then UV gets out here. So there's an evacuated cone, I really do need some UV photons to photoionize my line. So I can't have a situation of no ionizing photons, but I have a very narrow cone. So most of the time I observe these, I don't see much UV. Maybe 1 out of 100, I might see UV, and those are the UV quasars. I don't know, but that's the picture in this geometry. Then the idea is that you hit this opacity feature at 10 to the 4-ish, where you have to ionize N equals 2 hydrogen. And you lose support for this puffy disk structure, and the disk becomes then a thin disk. And so the outer part of the red part in this picture would be an outer ring of a standard thin disk. This notionally is the idea. Very, very notionally is the idea. And indeed, we see different peak temperatures in different prism spectra. So but I don't know. If we see Balmer absorption lines in the breaks, then maybe I'll give up the AGN only continuum model, and I don't know. We'll see.
Okay.
All right.
Well, thank you everybody for the questions. Before we thank Jenny, I'd like to announce next week's colloquium. And again, we're oscillating very much between stellar objects and galaxies in this series, but please come along. That's going to be a really interesting one, also in the context of dense stellar structures, which seems to be part of what the little red dots may be about. So the next slide is the next events on Jenny's schedule. And please, we thought originally we would have a student meeting directly afterwards, but Niels Hoyer will actually, if he can just make himself seen, we'll be organizing something tomorrow, I think. Or whenever, please contact Niels Hoyer if you're a student and you want us to have some informal discussions with Jenny. And then later this evening at 7 o'clock, we are going to go and have some dinner. So please announce yourself if you want to join as a last minute attendance to that, to Nadine. Yeah, Nadine. Okay, so thank you, Jenny, for this fantastic colloquium.